to my lecture today. Today we actually starting chapter 16, which is going to be the last chapter of the semester. And of course, the focus is going to be on Bayesian inference. Let me use this opportunity to say that we got two fundamental approaches to statistical inference. And of course, each with his own principles and methodologies. Now I'm going to say the one um, we've been doing before now is actually called frequencies inference. Okay, so I'm actually going to make a distinction between frequencies inference and Bayesian inference. Now, we talk about frequencies inference. Parameters are considered fixed, and of course, whatever estimation that we want to talk about will be based on sample data. But when it comes to Bayesian inference, we actually see parameters as random variables because we believe we got uncertainty in the parameter. And of course, estimation is actually based on combining prior beliefs with observed data. So the focus today is actually going to be on, you know, starting with prior belief, and when we get new information, if new information is actually going to come in form of data, then I will combine that with the prior belief. We actually going to have a posterior belief, a posterior distribution, which is the way the Bayesian inference actually work. Okay, so in the outline, you're going to be introduced to that, and I'm going to make a distinction between the prior and posterior distributions, because prior and posterior distributions are actually used in Bayesian framework. And of course, before now we've been talking about estimators. Every estimator we've been talking about before now, they actually consider to be frequencies one. Okay, the frequency is one because the parameter is assumed to be fees, while estimation is actually based on data. But in the base estimator, of course, a parameter of interest is not going to be assumed to be fees. It's actually going to be a random variable. And when it's a random variable, of course, we're actually going to have a probability distribution associated with our belief, which we call the prior. And by the time the new information is available, we're actually going to combine, that updates our belief with the new information. Okay, but you know what? Before moving forward, I would like to give you example of Bayesian inference in real life practical situation. I'm actually going to give you example from medical trials before moving forward. Suppose a pharmaceutical company, is testing a new drug. And of course, they actually want to use the new drug for treating a particular disease. Of course, if they want to use Bayesian framework, they're actually going to start with a prior belief about the drug effectiveness. Okay, and that will be based on preclinical studies. They'll be able to derive their belief from the preclinical studies. And do you know that after conducting clinical trials and observing patient responses, they will now update their belief about the drug efficacy. Okay, so that is the way it is applicable, in medical trials. Now, if I want to go into financial analysis, maybe predicting uh, price of stock, of course, they can actually, they're going to start with a prior belief about the expected returns and the risk associated with an asset. Of course, the risk associated with an asset is going to be a standard deviation of returns. Okay, and you know what, as new information becomes available, the new information could be about the quarterly earnings reports or the economic indicators, and they will update, their belief. Now, lastly, I'm going to give you an example from weather forecasting. The meteorologists actually use Bayesian techniques to update our weather forecast based on the observed weather data and computer models. What they're going to do is just like what I used to say. They're going to start with a prior beliefs about weather patterns and conditions, and that will be updated using data from satellites, weather stations, and other sources. And of course, the resulting posterior distribution, we actually provide a more accurate estimate of the future weather conditions. Okay, so we got a lot of examples of using Bayesian or inference or all of that. We start with a prior belief. In the case of frequencies that we've been doing all this why, that doesn't base on any prior belief. We normally go straight to data. Okay, now I want to start giving you, since prior belief is what make Bayesian inference to be different from frequencies inference. Of course, we're going to talk about prior distribution. Okay, so when I talk about prior belief, we actually believe the parameter of interest that we want to figure out. The parameter interest we want to figure out, could actually be proportion, it could be mean, it could be whatever population characteristics of interest that we want to figure out. Okay, so let me just assume that the parameter of interest that we want to figure out is a proportion. Okay, proportion P. Okay, maybe we want to know how popular is the president of the United States. Okay, of course, and before seeing data, okay, before seeing data, what is our belief about the popularity of the president? Okay, so that's going to come in form of a prior distribution. Okay, so we can only have a probability distribution for something that varies, because parameter proportion here is going to be assumed to be a random variable. We're actually going to have a distribution for that. Okay, now because of the fact that the um you know when the popularity of the president will lie between 0 and 100%, which means in terms of proportion, 0 and 1. Okay, if I want to talk about prior distribution, we can make use of a beta distribution, because you know why? Beta distribution lie between um 0 1. Okay, so for instance, if I have my f of p now, give me 1 second. Gonna clean that. I'm gonna write, because I'm using the g of p. So I'm actually gonna say my g of p now is gonna be p raised to power alpha minus 1, 1 minus p raised to power beta minus 1 divided by b of alpha beta. Of course, the p that I'm actually looking for is going to be a lie between 0 and 1. So the prior distribution that I'm actually going to use, on the proportion, a good one is actually going to be a beta distribution. So when you take a look at it now, a p is actually the proportion. Okay, the proportion here is a random variable, and alpha and beta are the parameters of the distribution. Okay, so if this is that, another thing that's if that serves as a prior distribution, okay, then I also need a likelihood distribution. Okay, the likelihood distribution is okay if I go to the data. If I actually go to the data and I actually want to figure it out, like maybe I go to the American population, I want to investigate, how many Americans approve the job the president is doing. Of course, he said that, you know, somebody say, oh, approve the job or not. So that's going to be Bernoulli. Okay, so if that is Bernoulli, Bernoulli distribution is actually, if I have P of S, okay, it's going to be P raised to power S, okay, 1 minus P raised to power 1 minus X. We are start from 0, 1. So that's a Bernoulli. So this Bernoulli now is actually going to be individual response. Okay, it's going to be probability distribution for individual because we got two possible outcomes. So that they say they approve the job the president is doing or not. Okay, and you know what? By the time we take the likelihood, because we're not going to investigate one person. Okay, so taking the likelihood of that now, what we actually, the sum of Bernoulli, because we actually want to count the numbers of Americans that approve the job the president is doing. So I'm actually going to have y equal to x1 plus x2 until we get to xn. Okay, which is summation s. Okay, the summation s, which is why we follow binomial distribution. Take a look at that. So what I'm trying to tell the world now, okay, this is going to serve as the likelihood distribution, okay, the likelihood distribution, which is actually the distribution for the data. Okay, and don't forget, before the distribution for the data, we have a prior distribution. Okay, we have a prior distribution for the parameter. Okay, so now we have that now, then let's now assume that maybe the we are assuming alpha to be 1 and beta to be 3, because if I want to, the beta distribution that I gave the other time, when I got to give a days equal to that, okay, we actually need to know the values of alpha and beta, which are the parameters in the distribution moving forward. Okay, now if alpha equal to 1 and beta equal to 3, you know what that implies? You remember, based on the characteristics of beta distribution, the expected value of P in that regard is actually going to be alpha over alpha plus beta, right? So which is going to be 1 over 1 plus 3, which is 1 over 4, which is 0.25 that you see here. The 0.25 here is actually going to be a prior mean. Okay, the prior mean based on the prior distribution before I collect data at all. So what I'm trying to say, 25 on average, 25% of Americans will approve the job the president is doing. This is before collecting data at all, before going to American population. Okay, this is what I have as this is my belief. You get what I mean? And uh, and this can be updated the moment data becomes available. So if I actually plug in alpha to be 1 or beta to be 3, okay, into this distribution now. So, that's going to be p raised to power. When I do 1 minus 1, okay, I'm going to do 1 minus 1, I'm going to do 1 minus p into 3 minus 1, they've divided by b into 1, 3. Okay, now this is going to be raised to power 0. That's going to be 1. 1 minus p raised to power. I'm actually going to have this guy. And of course, if I want to know b of 1, 3, okay, if I want to know b of 1, 3, you need to remember, the non-integral definition of a beta function. That's a gamma alpha, gamma beta divided by gamma alpha plus beta. So, and of course, if I want to do b into 1 comma 3 now, so I'm actually going to have gamma 1, gamma 3, all divided by gamma 4. Okay, and when that happen, you're actually going to be that gamma 1 is 0 factorial, gamma 3 is 2 factorial, gamma 4 is 3 factorial, and this is going to be 2 over 6, and that's going to be 1 over 3, and that's also why we got this 1 over 3. So 1 divided by 1 over 3, that's going to be 3, and at the end of the day, so that was how we actually got what is here. So, based on alpha equal to 1, beta equal to 3 now, our prior distribution G of P is actually going to be equal to 3 into 1 minus P all squared. Okay, that's a prior distribution. Okay, now, you know, if I combine the prior distribution here, okay, I'm actually going to do something now. Our prior distribution here is 3 into 1 minus P all squared, right? Okay, I'm actually going to stop my share. I'm going to share my whiteboard. I just wanted to see. Okay, I'm going to share my whiteboard. Give me 1 second to do that. Okay, now, sharing my whiteboard now. Okay, I already have the G of P, which is equal to 3 into 1 minus P all squared. Okay, so P lie between 0 and 1. Okay, and of course, there's a prior distribution, right? Based on alpha equal to 1, beta equal to 3. But you know what? What about the likelihood distribution I told you the other time? The likelihood distribution is actually going to be the likelihood function of a Bernoulli. Okay, so f of y given p is actually going to be p raised to power y. Okay, and 1 minus p raised to power n minus y. Okay, don't forget that our y is actually summation s. Okay, so this is a likelihood now of the Bernoulli distribution. So if I want to get posterior distribution, okay, because in Bayesian analysis we normally combine the prior distribution with the posterior distribution. So it's more or less like we are updating our belief initially with the new information, which is the data here. And of course the likelihood distribution is actually the data distribution. Okay, so I'm going to say my posterior now is going to be f of p given y. Okay, it's going to be you're combining the g of p with the f of y given p, then divided, by the total, the total, because the f of p given y is a probability, right? Then it's going to have a total. The total is going to be, I'm still going to have, right, this guy here, you know, I'm going to integrate that with respect to that, the p. Don't forget, our proportion, the parameter is a random variable. Okay, so this is how to get the posterior. So this is a prior, like I said, a prior distribution. This is a likelihood distribution. Okay, and this guy here is actually posterior distribution. Take a look at that. Now, what I'm going to do now, I'm actually going to be using the formula. Okay, I'm going to combine that guy with that guy. So 3 into 1 minus p squared, then 1 minus p raised to power n minus y. Okay, you can see them multiplied by that. So I'm actually combining this guy and this guy. You can see what I have right now. And I'm also going to integrate that guy here, 3 into 1 minus p squared, okay, py, okay, 1 minus p raised to power n minus y, okay, dp now, okay, now because I'm actually integrating with respect to p, okay, I can cancel out anything that is not this guy is going to be a constant. That guy can go away. This guy is going to be a constant. Okay, that is no longer going to be part of what I want to do. And moving forward, I'm actually going to combine this and that. Okay, so let me do this. Let me say what I have right now is actually combining that and that. So let me just say I'm gonna have p raised to power y, 1 minus p raised to power n minus y plus 2. Okay, now divided by integral of that, divided by integral of the same thing. Okay, because I need a room, let me just write up here because I need a room. So I'm actually gonna clean my board now so that I can have a room. Okay, so take a look at this guy now. So my f of p given y is actually like I said, combining that, I'm actually gonna have a p raised to power y, and I'm gonna have 1 minus p raised to power n minus y plus 2. Okay, and you know what? If I have that, that is what I'm also gonna have in the denominator. Okay, except that I'm gonna be integrating that. So using that, the integration of that is going to be a marginal that I'm actually want to get. So going to be 0 to 1 of p raised to power y, 1 minus p raised to power n minus y plus 2 dp. Okay, now I want to focus on this guy now. If I want to focus on that guy, I actually need to recall from, recall now from a beta function. Okay, that's what we call a beta function. Okay, in a beta function, when I have a b of alpha comma beta, it's actually going to be 0 to 1. Okay, p raised to power alpha minus 1, 1 minus p raised to power beta minus 1 dp. Now, when you take a look at this, when p carry alpha minus 1, if you add 1, that's going to be alpha here. And on this one, when I 1 minus p carry beta minus 1, so when you add 1, it's actually going to be that. Now, take a look at this. So, we want to write that in a using a beta function. Okay, integral definition of a beta function. So if I'm actually, that's going to be, so here our p is carrying y, so it's going to be y plus 1, right? And here 1 minus p is carrying n minus 2 plus 3, then you're going to add 1. So the exponent is going to be n minus y plus 3. Okay, so what am I telling the world? What I'm telling the world now, so this guy can replace this guy here. So I'm gonna clean it up now, and I'm gonna put that guy. Okay, I'm gonna put that guy. So putting that guy now, I'm actually gonna write y plus 1 comma n minus y plus 3. So take a look at that. So that is what I'm actually gonna have right now. Now, if I have this guy right now, then I need to also remember something that we call the non-integral definition. The non-integral definition of a beta function. Okay, of a beta function. Okay, the non-integral definition of a beta function, if I have this of that, is going to be gamma alpha, gamma beta over gamma alpha plus beta. So if I want to do this guy now, so I'm going to do y plus 1 comma n minus y plus 3, and I'm actually going to have gamma dap gamma this, okay, divided by gamma. So I need to add that up. So y cancel y, then I'm actually going to have n plus 4. So take a look at that now. Okay, now if I want to put that, so it means I'm actually going to put this guy here now. Okay, if I put that guy here, of course, I'm actually going to have, let me clean up now. So I'm actually going to have, when I put that guy, I'm actually going to have gamma y plus 1, okay, gamma n minus y plus 3 divided by gamma n plus 4. So when I simplify, okay, you're going to see that the gamma n plus 4 is going to go up. Okay, gamma n plus 4 is going to go up. So you're going to see now. So finally, I'm actually going to have gamma n plus 4, okay, p raised to power y, 1 minus p raised to power n minus y plus 2, then divided by gamma y plus 1, gamma n minus y plus that. Now, this is what we call posterior distribution. Okay, this is a distribution we got when we actually update our belief with new information in the data that is combining the prior distribution with the likelihood distribution, and they actually give us a posterior distribution. If I want to make an inference now, if I want to make Bayesian inference now, this is the distribution that I'm actually going to use. Okay, so that is how we derive that. Okay, so I'm gonna go back to the lecture slide. Give me 1 second. I'm gonna I'm gonna share that now. I'm gonna share the lecture slide once again. Okay, so share me the lecture slide now. So we've been able to derive this. You can see that was what we derived, which we call posterior. Okay, that was what we derived. Now, if you take a look at this posterior and you know, the one that the prior, they actually belong to the same family. Okay. If you take a look at this posterior and they belong to the same family, and because of that, I'm actually going to call that prior conjugate. Okay. And comparing the posterior density with the prior density now, we're actually going to see that our alpha is y plus 1 and our beta is actually that. Okay, so that's gonna, because if you the one we have before, when you want to talk about the prior, okay, the prior is actually going to be p raised to power alpha minus 1, 1 minus p raised to power beta minus 1. Okay, and you know we're writing that this is going to be gamma alpha, gamma beta, and here give me 1 second. Let me create a space. So, here I'm actually going to have gamma alpha plus beta, after, expressing that, in terms of the non-integral definition of a beta function. Now, if you want to compare now, you're going to see that this guy here is alpha, and this guy here, okay, is our beta. Can you see that? Okay, situation where the posterior belong to the same family of a prior, that will be called a conjugate. I'm actually going to write that. We call that conjugate. We call that kind of prior conjugate. I say conjugate prior. A prior is going to be conjugate if the resulting posterior distribution, they are in the same family with the prior. Okay, we normally want that all the time, because of simplicity and and trackability. That is a reason. But you know what? It's not all the time that the posterior belong to the family of a prior. When that doesn't happen, of course, we're actually going to resolve into simulation moving forward. Okay, so now this is the general idea. I'm going to give you the general idea now. Okay, we actually, if you take a look at this is a likelihood. This is the prior distribution. And this guy here is a marginal density. Okay, the marginal density, is that is what you're going to have in the denominator. So, which is integrating, we're integrating that with respect to theta, okay, in general form. So now when you take a look at this guy now, so that is a posterior density. Now I needed to pay attention to what you have. Look at the numerator here is what you are integrating here. So it's just a general formula, okay, for the posterior. So when you are given any probability distribution, if they wanted to derive posterior density, you actually need to you're going to make use of this formula, combining prior distribution with a likelihood distribution. Okay, so take a look at that. That's the general formula. Okay, so this is synonymous with what we did the other time. You have a Bernoulli, for the data. Okay, where the probability of y1 equal to p and y0 equal to 1 minus p, of course. I was discussing the other time the popularity or the approval rating of the president of a country. Okay, uh, when I select a random sample of y1 up to yn, each of them has a possible outcome. So it's either they actually approve the job the president is doing or not. So we got to have a label in 1 and 0, because that is binomial in nature. Okay, so and they're assuming a prior distribution is a beta, just like what I did the other time. Find the posterior. Of course, this is what I did the other time. This is a likelihood distribution. Okay, so that is a Bernoulli. You find the likelihood of the Bernoulli. The likelihood of the Bernoulli is actually going to be that. Of course, you remember before I've worked it through how to find the likelihood function, given a distribution, how do you find the likelihood? So the idea of the likelihood is very, very crucial when it comes to Bayesian framework. So you must be able to understand how to get the likelihood of the probability distribution of the data. Okay, the probability distribution of the data here is actually Bernoulli. Then you get a likelihood. That is a likelihood. Okay, and they gave us that the prior distribution is actually beta. Okay, so take a look at that now. So this is the prior distribution, and this is a likelihood. We multiply them. Okay, now when you multiply them, it's actually going to give you this guy. Don't forget, you have to go back to high school, like remembering what you did in algebra, where you're going to combine some terms together. Okay, so we're going to have this. And don't forget, when you have this, we're actually going to have the total where you integrate this, then you're going to use the total to divide out. So that's what we're going to have here. Take a look at that. Okay, this is going to be the total now. I'm integrating with respect to, the limit 0 to 1, because that is going to be the range of P. Don't forget, the parameter P is the proportion is going to lie between 0 and 1. Okay, now let me handle the total first. When I handle the total first, okay, integrating with respect to P. Okay, anything other than P is actually going to leave, this guy is going to leave, right? Which is what we have here, right? Now, if you focus, let's say this guy is out, focus on the remaining one. You can use a beta function. And I told you the other time, the integral definition of a beta function. So this guy, you're just going to add 1 to the exponent. That is going to be b of summation y plus alpha. Okay, then the other one, add that one to the exponent. That's going to be n minus summation y plus beta. Can you see that? That is what we're going to have. Now, you now need to write this in a non-integral form. In a non-integral form, it's going to be gamma summation y plus alpha, gamma n minus summation y plus then divided by the gamma of addition, which is what you have here. Can you see that? That is what we have. That is what we got. Now, by the time you now go back to the posterior density, where you now, this is what you're going to have now, which is going to be, the product of the likelihood and the prior divided by when you integrate that. By the time you simplify that, of course, that is going to lead you to this. And leading you to that, you can actually see that if alpha and betas are the parameters of the prior distribution, then we need to also obtain the new parameters for the posterior. Okay, so when you take a look at this, and because this guy is in the same family with a prior, okay, is in the same family with a prior distribution. Don't forget, the prior distribution is actually beta, okay, which I'm going to write that now so that you're going to have opportunity, to come, to actually compare that. That's going to be gamma alpha plus beta, gamma alpha, gamma beta, p raised to power alpha minus 1, 1 minus p raised to power beta minus 1. That is the prior, right? Compare this with that. You're actually going to see that our alpha, okay, our alpha star, okay, if you compare that, is actually a summation y plus alpha. So if you take a look at this guy, okay, and this guy, then it means your alpha is summation yi, that is your new alpha, which is called alpha star. Alpha star with star alpha, that is for the parameter of the posterior. Then the original alpha is the parameter of the prior. Okay, now take a look at that. Then our new beta is actually this guy here. That was why we got that. So right now, we got new parameters. Take a look at that. The alpha star and the beta star are the posterior parameters. Does that make sense? Take a look at that right now. Okay, so if that is the way we do it, okay, that is the way we do it. Okay, so what I'm going to do now, I'm going to move to the next slide. Now, let us have an example now. Okay, consider the virulent disease scenario and the results of example 16.1. We want to compare prior and posterior distributions of a Bernoulli parameter P, the proportion of responders to the new therapy. It is not every patient that will respond to medical intervention. Okay, we want to figure the proportion of patients that are actually going to respond to the new therapy that will be proposed. Okay, now I'm going to walk you through this example. You know, um, when alpha equal to 1, beta equal to 3, n equal to 5, summation y equal to 2, of course, this is going to give us opportunity to compare the prior distributions with the posterior distributions, and to be able to justify that Bayesian inference work, we're actually going to see the shape that is going to bring out, okay, and that very shape we want to see whether it's going to spread out or it's going to shrink in. So we actually going to see right now. Okay, now if I consider in the first one, when alpha equal to 1, beta equal to 3, if I want to consider just prior distribution, I only need alpha and beta. I don't need n. I don't need summation, because when working with a prior, we do not have knowledge of the data at the time. Okay, now if I want to get a prior mean, okay, because alpha equal to 1, beta equal to 3, so, and I know the mean of a beta distribution is alpha over alpha plus beta, so the prior mean here is going to be 0.25. Okay, and based on what we've done before, the maximum likelihood for by Bernoulli is P cap is summation y over n, and they give you summation y to be 2, n to be 5 in the data. It means your P cap is actually 0.4. Now, after getting that, do you know we can also figure out the parameters of the posterior? You remember the other time right here, you know, I can figure out the parameter of posterior because I know summation y and I know alpha. So I can figure it out, the parameter of posterior. So that's what I'm doing here. Take a look at this guy. Okay, take a look at this guy. Can you see that? Okay. If alpha equal to 1 and beta equal to 3, this is what we're going to have as posterior parameters, alpha and beta star. Okay, I needed to take a look at that. So that answered the first question. So if I want to answer the second question, the second question actually said when alpha equal to 1, beta equal to 3, we are still using the same alpha and beta, except that we are changing the sample size. Okay, we actually, we also want to see the way the prior and the posterior will respond to change in sample size. Like when I increase my sample size from 5 to 25, and my alpha is still 1 and beta is still 3. And of course, when summation y go from 2 to 10. So we want to see what happened. Okay, so of course, we're going to have opportunity to determine the alpha star and the beta star that are posterior parameters. I need to take note of that. Okay, so we can generate a table for that. If you take a look at this table, it's going to give you opportunity to be able to figure out what is a prior mean and what is a prior variance. Okay, of course, here when n is not given, summation y is not given, we can only talk about prior. Okay, because prior, is prior distribution is the probability of the state of nature before collecting data. So now, of course, we're actually going to get it because the mean is alpha over alpha plus beta. And then I think the variance is alpha beta divided by alpha plus beta squared, alpha plus beta plus 1. I think let me write that. If I have the mean is alpha over alpha plus beta for beta distribution. The variance is alpha beta divided by alpha plus beta or squared alpha plus beta plus 1. Okay, now that is what we use. We use this particular formula here to get this. So there's a prior variance. Okay, this is prior variance. Don't forget, we're talking about prior. This is prior mean. This is prior variance. Do you know? I can find the posterior mean, posterior variance. How? Okay, the posterior mean is just going to be alpha star divided by alpha star plus beta star. Okay, while the posterior variance is going to be alpha star beta star divided by alpha star plus beta star squared alpha star plus beta star plus 1. Okay, when you plug in all of that, we actually gonna get. So this is gonna give you opportunity. There's something I need you to see. Okay, this is a prior variance. This is posterior variance. You can see posterior variance is less. If you compare the posterior variance with the prior variance, we're actually going to see the posterior variance is less. And when sample size goes to 25 from 5 and summation y go from 2 to 10, you can see the posterior variance shrinking. Okay, and in statistical analysis, statistical inference in general, we focus on the variance. You understand what I mean? So now, this is actually telling us that, okay, using prior information, this is actually gonna work. Okay, so take a look at that. Okay, I think I'll give other examples. So now we can take a look at the shape right now. So this is the graph of a beta priors. Okay, as you can see, when for the first scenario is when alpha equal to 1, beta equal to 3, you can see the shape. And when alpha equal to 2, beta equal to 6, you can see. And when alpha equal to 11, beta equal to 18, you can see this actually confirm the flexibility of a beta distribution. Okay, let's look at the posterior. Oh my God, look at the posterior right now. If you compare this with this, you're actually gonna see that of the prior is more spread out. Okay, more spread out. More spread out means more variability. Okay, which means more variance, right? Take a look at the other one. This guy here shrinking, which is actually confirming to you that the idea of a Bayesian walk, okay, compared to the just prior, take a look at this guy, and that actually confirm this guy here, because you can see the variance of the prior is higher than that of the posterior. The variance of the posterior is smaller. That shows an improvement, right? But let me tell you this, we don't just compare variance directly. I'm still going to walk it through because the idea of in Bayesian inference, the Bayes estimator could be biased, and in that regard, we may be talking about the mean square error. After taking into consideration that, but that's not a big deal. Okay, I'm still going to talk about all of that. Okay, now for this, I'm going to reserve this Bayes estimator for the next class. Okay, I'm going to reserve this for the next class. Okay, make sure you all stay safe and have a lovely day. So bye for now, everyone.